All right, these are your notes on quadratic systems, solving them algebraically as well as graphically. It's going to stray from the beaten path, and it's actually going to follow some text from both Glencoe as well as one that's not Glencoe. So the examples I'm about to do are in a different textbook found in the Unit 2 tab on Task Stream. Notice that there's this little three blank chart where you're going to draw the diagram of how many possible solutions you could have in a linear quadratic system. In example 1, it's asked to solve the system by graphing, but I'm actually going to do this algebraically just to prove the point that you can still solve for intersection points by using normal system methods. Notice that I have these two equations and they are both set equal to y. Because both of my equations are set equal to y, I can set their other parts equal to each other. So x squared plus x minus 2 is equal to negative x plus 1. Anytime I see a quadratic term appear, I know that I need to get my equation set equal to 0 to solve it. So I'm first going to add x onto both sides, and I'm going to subtract 1. So we get x squared plus 2x minus 3 equals 0. One of the methods for solving quadratics is by factoring. So let's see. We have an x, and I'm asking myself, what multiplies be negative 3 but adds be positive 2? Well, that would be positive 3 and negative 1, okay? When I set both of my factors equal to 0 by the zero product property, I get solutions of negative 3 and x equals positive 1. So these are the coordinates, the x coordinates where I intersect. Now to find the y coordinates, all I need to do are plug both of these values for x into either one of my equations. In this case, it'd be a lot easier to plug it into the linear equation. So when I plug it into the linear equation for my first coordinate, I get a y value of, it was negative 3, so that becomes positive 3, which equals 4. So I intersect at a point negative 3, 4. When I plug in 1 to my linear equation, y is equal to negative 1 plus 1, which is 0. So we also intersect at 1, 0. Now I do want you to also attempt this graphically, but why don't you graph both of these on your own, get some good practice, and you know you're going to have the right system so long as they intersect the two coordinates that I found for you algebraically. Alright, so you're going to notice that I actually only require that you do the first two examples for your quadratic linear system notes, but please recognize that there's actually a lot more examples, so if you're needing more assistance with linear quadratic systems, please continue reading. So in this next one, we are going to, again, we're going to solve this algebraically, and because they're both set equal to y, I can set their equations equal to each other. So we have 2x squared plus 3 equals x plus 2. Once again, because I see a quadratic term appear, I want this to be set equal to 0, so I'm going to subtract x onto both sides, and I'm going to subtract 2 from both sides. And so we now have this quadratic here, okay? So let's actually solve this by using the quadratic formula. So we have negative b plus or minus the square root of b squared minus 4ac all over 2a. So our b value is negative 1, so we have negative 1 up front, so it's a positive 1. Then we have negative 1 squared is just 1, minus 4 times. My a value is 2, and my c value is 1, all over 2 times my a value of 2. All right, zoom out a little bit, give myself some more room here. All right, so when we keep solving in this, we're going to see 1 plus or minus. Notice that underneath my radical, it's going to produce a negative number. This means that I have imaginary solutions. So if you were to graph this, you would not see them intersect at any coordinates. But it does mean that they still intersect in the imaginary plane. So we end up with 1 minus 8 under our radical, because this term right here is going to be 4 times 2 times 1 is 8. And 1 minus 8 is negative 7. So our simplified answer becomes 1 plus or minus I radical 7 over 4. There are their two intersection points. All right, so now we're actually going to take a peek into 8-7, and we're actually going to need to revisit the topics in 8-7 once we start getting into conic sections, okay? So here we have these two equations. We have x squared minus 4y squared equals 9 and 4y minus x, and we're going to solve this algebraically, and we're actually going to use the substitution method by getting this equation set equal to x by adding x onto both sides and subtracting 3. So if I rewrite our equations, we have x squared minus 4y squared equals 9. And this next equation became 4y minus 3 equals x. So I'm actually going to take this quantity that's equal to x and substitute it into x into our first equation. So we have 4y minus 3, that quantity squared, minus 4y squared equals 9. And so now I'm actually going to FOIL my expression here. So for the quantity 4y minus 3, that produces 16y squared. That's also going to produce, we're going to have 2 negative 12y, so negative 24y. And then we're going to have a positive 9, okay? And we still have a minus 4y squared. Now we're going to combine like terms. We're going to subtract this 9 over here, getting me a 0. We have a 16y squared and a negative 4y squared, so that's going to be a 12y squared minus 24y equals 0, okay? Now, if I were to divide everything by y, what would end up happening is I would lose my solution. So I actually need to factor out the y from both terms here. But the other thing I can do is I'm going to divide everything by 12 so that this becomes just y squared and this becomes just a minus 2y. So when I factor out a y from both terms here, I'm left with y minus 2. And then once again, I can use my product property here. And I'm going to get solutions of where y is 0 and where y is 2. Now notice here we actually got the y coordinates first. So now we can plug these values into our linear equation to find our values for x. So we have, first off, 4 times 0 minus 3 equals negative 3. So one of our coordinates of our solutions is negative 3, 0. Then if I plug in my next one, 4 times 2 minus 3, that's 8 minus 3, which is 5. So our next one is 5, 2 for our two solutions for this system. Notice that once again there is a table for you to fill out on this page where you're actually going to draw some shapes just to help you kind of recognize where we are headed in our journey with conics in Unit 4. All right, this is the last example, and then once again, we're going to revisit this topic later. And I'm actually going to use my elimination method. So I'm actually going to bring my x squared onto my left-hand side of the first equation by adding him. So we change the first equation to x squared plus y squared equals 13. And I haven't touched the second equation here, okay? And so what I'm going to do is I'm going to subtract these two equations. So x squared minus x squared cancels out. Y squared minus negative 4, oops, I changed that sign. That's a plus 4y squared. So y squared minus 4y squared becomes negative 3y squared. And 13 minus 25 becomes negative 12. Now I'm going to divide both sides by negative 3, so y squared is equal to positive 4. And when I take the square root of a quantity, it actually produces a positive or negative solution. And the square root of 4 is positive or negative 2 here, okay? So now what I need to do is I need to plug in both positive 2 as well as negative 2 into either one of our systems. All right, so let's actually use the very first one. Y squared equals 13 minus x squared. So first off, when we plug in positive 2, we have 2 squared equals 13 minus x squared. And then I'll just show my work. That way I'm setting up, and I won't forget my solutions here. All right, so 4 is equal to 13 minus x squared. When we subtract 13 from both sides, 4 minus 13 is going to get me negative 9 equals negative x squared. If we divide both sides by a negative, it just becomes 9 is equal to x squared. Then once again, we're going to take the square root of both sides, getting me a positive or a negative 3 as my solutions. So then the coordinates where I intersect are 3, 2, as well as negative 3, 2. Okay? So then on the next problem, it's actually going to be solved the exact same way, because notice that these two equations actually became the same, which means it's going to produce the same values for x. But remember, we were actually using a y value of negative 2. So that gives me two new coordinates of 3, negative 2, and negative 3, -2. So notice in this problem I ended up with 4 solutions.